Good morning. Thanks for coming here on the weekend. So about a month or 2 months ago, Gabi put the program together, and then lo and behold, I looked through it and I thought, I'll just find a kind of empty spot with the title of my talk and then I can think about it. But no, Gabi did the work for me. He made a title, but then I kind of thought, wow, what do I do with this? Life with an altitude, a biosphere-atmosphere perspective. And so I went to Gabi and said, can I change it? And he said, no. You have to find a way to deal with it. So here we go. So of course I thought, life with an altitude has to be something flying. And this is a golden eagle in Dubai. And the golden eagle is flying very high and sees just about everything. Circles, looks around, as you can see. Sees the desert, the city, the buildings. Has a very, very large field of view. But not only that, the eagles are world record holders in the way that they can see very far and have a huge field of view, but they can also spot in on tiny little details. And you'll see what happens when the eagle sees something that is of interest to him. This is a trained eagle, and there we go. The thing he was interested in is his trainer, and there he is on the ground. Apparently this was a world record flight of diving down, I don't know, several hundred meters. Didn't quite go from the top of that building. So the eagle's perspective is how we want to start. The eagle has a huge field of view, much more than a hemisphere. Not only that, I mean, you can see just everything except for a little blind spot. Of course, the eyes on the eagle are on the side. But it has a fairly wide field of view also, where it actually sees things in focus at the same time as seeing the rest. And only this very, only around here, it only detects motion and doesn't really recognize what things are. So it can spot a rabbit 5 kilometers away. That's quite impressive. It would be equivalent to reading in the newspaper that's on the other side of a soccer field. Try that. So it can concentrate on a detail while keeping the rest of the world in view. We can do that too, but not as well. So let's have a look. Do this experiment with me. Focus on the rabbit, and it'll work better for the people in the front than the people in the back. Look only on the rabbit, okay? Did you see it? Well, if you saw an E, which shape was it? There were 2 E's. Okay? But maybe you cheated, because we can cheat. We can move our eyes to the point of interest. The E on the left was actually lying down, right? So we can cheat. But flux sensors, for instance, cannot cheat. They cannot do that. So how do flux sensors see the surface? And how can we make them see what we want them to see? How can we assure the flux sensors see what is of interest? Step back a bit. How is this relevant? If the surface is homogeneous, then it doesn't matter. If there are rabbits everywhere, you see a rabbit everywhere and it doesn't matter. Because then they sense the same thing anywhere. But if it's inhomogeneous, then we have to ask ourselves, okay, with this field of view thing, what is actually homogeneous? What is inhomogeneous? Not just for us, but for a flux sensor, if we're interested in fluxes. So is this homogeneous or inhomogeneous? Do you get vertigo when you look at it? A little bit, huh? Well, it has aspects of both, homogeneity and inhomogeneity. So we'll talk a little bit about surface-atmosphere exchange over inhomogeneous terrain. It's funny, I cannot see it, I cannot read it here, I can read it there. Or we can say we're trying to see the forest for the trees. Here is a picture of the forest where I spent one of the best parts of my life over, the Morgan-Monroe State Forest in Indiana. Here is somewhere where I have not been, Timbuktu. The forest, you can see it's extensive. We often called it a homogeneous forest. You can see some structure in it. In Timbuktu, you can see some aspect of homogeneity. It's just buildings, but they're not very regular. What about this? This is a vegetation called Tigerbush. It's just one aspect, one little bit out of it. Is this homogeneous? And then this is a suburban area in Markham, Ontario. So it's about pattern and scale. And the atmosphere sometimes organizes itself into patterns and sometimes even distinct spatial scales. It's something that was mentioned, I think, by Matthias yesterday, the roles, the way eddies organize themselves. Sometimes you can see it by clouds formation. And sometimes those patterns can stay or travel together very slowly. A bit like that. This is from an album of fluid dynamics. But then we actually often change the landscape in a way that we impose scales that may or may not have an effect on the atmosphere. That's what we are going to explore a little bit. Sometimes the patterns look like this, and sometimes they look like that. And sometimes they look like this. This is actually also imposed by people because it's a forest fire. And there was a forest fire and there was a bark beetle attack in this area of actually the Bavarian forest. So is this forest homogeneous? Well, at what scale is it homogeneous? That's really the big question. You can see here in the middle is a tower. The tower we built to do measurements, and on top of that we have an eddy covariance system. It's still there for over 20 years now. So it doesn't really matter whether I perceive it as homogeneous or not. It really matters whether the sensor system perceives this as homogeneous or not. So let's look at something else that has very, very well-organized scales. This is a suburban area of Mexico City. I don't think I'd want to live there, but it serves the purpose well. And when I started my grad studies, I was in a community of urban meteorologists, and they talked about urban areas like this or suburban areas like this. And we looked at pictures like that to see where could we cite measurements and so forth. And then my supervisor was speaking about homogeneous suburban area. And I knew exactly what he meant by, intuitively I knew what he meant by homogeneous urban area. If you live in an urban area like this, it doesn't really matter. This block looks like this one or like that one or like this one. It seems that doesn't seem very individual. You could easily get lost because everything looks the same. But on the other hand, it's clearly not homogeneous. You can clearly see streets, you can see houses, you can see bigger ones, smaller ones. Even the streets, if you look closer, have actually a little bit of a difference. And so it depends on your resolution, on the scale of your observation. If I just put in a blurring effect, and that just means I reduce the resolution by actually moving a tiny little speck down here as a kernel of a low pass filter, move that over, then we still see the most important structural elements of this city, the streets, and we can see still the larger elements in the blocks, in the city blocks as well. But this is a very tiny filter. If we make this filter bigger, then we still see only the smallest, the biggest ones. And if we progress, we can hardly see a grid anymore. We can just only guess there's a little bit of a grid. Even more, we can just see the very large trends maybe. And if we go to this one, I did the statistics of it. It's essentially gone. It's a homogeneous field. Okay? So if our point of view or our perspective is such that we see always that much at the time and that we average over an area like this, then this city is homogeneous. If we detect things like that, or even finer scale, then it's clearly not. So it always depends on your scale, your perspective on an area to see whether it's homogeneous or not. You cannot separate the concept of homogeneity or inhomogeneity from the concept of scale. So let's go to plant-environment interaction or biosphere-atmosphere interaction. And for instance, for CO2, there is a vast range of well, it's not so vast, but there's a range of observational techniques, from the microscopic approach to the macroscopic approach. The microscopic approach was shown a little bit by Nadine, and the macroscopic approach you've seen many times, for instance, also with Matthias yesterday. You're interested in something quite a bit different. In the microscopic approach, you may be interested in actually transport between the inside of the leaf and the outside. And on the macroscopic approach, you're interested in not only a leaf, but a whole collection of them, and actually a whole collection of plants and the ecosystem as such. Timescales are also different that you're usually interested. And there are various ways to look at these interactions in intermediate scales. For this, we might use a cuvette, an enclosure, to just isolate the portion that we want to look at and look at that in detail. Even in a controlled environment, we can control the temperature, we can control the radiation if we want in there, and so on, and turn this into a little lab. On this side, we don't do that. The most common way to look at it is through an eddy covariance equipment mounted not at the tree, not in contact, but high above. And again, when the eagle is flying high, has a bigger perspective, bigger field of view than coming close down. And that turns out to be similar for meteorological sensors. So we have a surface of some kind, and then we are interested in, let's say, CO2 exchange, and we throw a tower in with maybe several levels of sensors on it. And at some point, there is a source. Let's assume that the mean drift is from the right to the left here, and the source produces something that goes into the atmosphere, in this case maybe CO2, and we want to examine whether we can capture that. Okay, individual particles, of course, they're subject to turbulent exchange, and they move around in this erratic fashion. Some of them will go to the left, and some of them will go to the right of the sensor. Some of them will take a long time to reach that height. Some actually may go the other direction for a while. And so we have something like that. And there is for a point source down at the surface, there is a probability that a particle will not only go by the sensor, but actually will impose a contribution to a flux there. Either it's moving upward at the same time, or it's moving downward and have contributions to a flux that we then count over half an hour or an hour and do the equivariance with. If the source is moving, then of course the probability of particles reaching the sensor changes as well. So we can find a kind of probability distribution on the ground. Which places on the ground have the highest probability that the material released from there will reach the sensor and contribute to a flux? That's called the flux footprint, this probability distribution. So the flux footprint is the equivalent to the field of view of the sensor. In the center of it, I won't step over the line here. In the center, the probability is highest, and so that means the sensor ability to detect something on the of the source behavior on the ground is the most acute. If you go further away, then the resolution, if you will, is lower. If something happens there, the sensor sees it, but only a little bit. If we have a forest as well, then things become more complicated, but I won't go into that. I think that's John's topic. I think you've already talked about it, right? Turbulence in canopies and so on. So, so the flux footprint is a tool that helps us to address the question, what part of the ecosystem does a flux sensor see? And then we can also, in the interpretation after doing flux footprint modeling, we can ask, is that part of the ecosystem that is sensed by our instrument, is that actually representative of the ecosystem that we are interested in? Do we have any chance to use our measurements and compare it with something like a model that doesn't take individual trees into account, but is usually representative of a larger area? For instance, 1 kilometer by 1 kilometer, if you compare it with something that is derived from MODIS or even coarser. So if that second question can be answered by yes, then we can use the data. If it's not, then maybe we cannot use that data, at least not for that specific purpose. So it gives us, it's a tool also to discriminate between data that we can use, that we can give, that help us to give the model a good chance to actually be correlated with the observations, and those that are not. Oops, forgot to put that math reader on it. So the equation up there looks a little strange, but you can read it up in the paper that I gave down here. The footprint actually is, well, the important part is still here. So here we have the flux of a location X as it is sensed by the sensor, and it relates to the flux source at a distance x from that sensor, and the source strength is given by QS here, and then the whole thing is folded, or it's a convolution of the flux is a convolution of the source strength field and the footprint. That's how the footprint is really defined. And here is just a more complicated way to express that convolution by the integral. So this is almost a cartoon. Most of this footprint will be in the upwind direction because the particles that come from a surface source will largely drift downwind, but it's actually possible, especially in convective conditions, low wind conditions of high turbulence, that you will have particles from behind that may drift past the sensor as well, but only very few. And only very few footprint models can actually handle this. So the dependence of this footprint doesn't matter which model is used. The strongest dependence is usually the height. So by choosing a measurement height, you can also control quite a bit about what the sensor actually is influenced by and what not, to stay away from influences far upstream that you want to avoid, a lake or something like that. But also not be too close to the ground so that you actually see an average of the conditions that you are actually interested in, so that you can have a chance to interpret your measurements. The other things that play into this is the roughness length, anything that actually influences the turbulent structure in your vicinity. So roughness length, U star, so the shear or friction velocity, and then in some models you also need statistics of vertical and horizontal wind fluctuations, and some models can actually deal with the entire mixed layer, and then they need an information about the boundary layer height. So those are the most common inputs to footprint models. Footprint models are tools, and so let's just assume we have that. And what I'm showing now is an application of this tool. And I'm using the model that I made myself a long time ago. To be frank, it's not the best. It was one of the first, but it's just the one I used. And let's just assume it's correct, okay? So we're looking at the spatial representativeness of flux measurements over inhomogeneous areas. And this is largely work that I did together with a colleague from now CEH, then Institute of Hydrology in Wallingford, Britain. And he was participating. Unfortunately, I couldn't participate in an exciting experiment, a hydrological atmospheric pilot experiment. Gabi mentioned the first rendition of that, which was Hapex Mobili in the wine-growing region of France, and because they had such a good time there, they thought we can't justify to always go to wine-growing regions or we start to be unbelievable, so they decided to go in more desert-like regions in the Sahel and a few years later. So 91, 92 was this experiment, and some of it was done in Niger, in the Sahelian region of Africa. And this Tigerbush, this particular vegetation pattern was at a site just a little bit south of Niamey, the capital of Niger. So the question of spatial representativeness and the location bias comes if we want to do measurements in there. Let's say we put a tower up and that has some sort of footprint, some sort of field of view. Does it matter whether I put the tower there or there? Do I get different things? If I do get different answers, then I'm certainly not interested in this particular patch or this combination of sand and bush. I'm interested in the whole thing. Okay? So do I need to go higher? Does it matter? Or do I actually capture it? That's the question that we want to answer. And so the flux location bias, I defined following a colleague, Carmen Napo. We're looking at something that is the flux that would come from the whole average area. Right? And the deviation that I get from being in a certain location, location X. What is the difference between those two? Look at the square, and then we scale it with the square of the total average. And that we then call delta, and of course delta, whoops, where is it? Delta is a function of that location. So this is the location bias. Oh, this is what I just said. Okay, and then we can determine, okay, so there's a certain limit that I tolerate of this bias. What is that? And if that location bias is smaller than that, then we can say, okay, it is representative or it is not. So this is a criterion for deciding a measurement is representative for my purposes or not. Stylized, this Tigerbush area is not completely homogeneous. You can see a sort of several scales of banded structure on the left-hand side, and we decided to just have two types of surfaces, either sand, rather dry, or then bush. And the bush has those trees, small trees, they have the ability to spread their roots and actually access water from quite far away. Is one of the reasons why this pattern is actually formed. And if the whole area that we look at here, just this square, has 46.7% bush and slightly more, 53.3% sand. In the middle, on the left-hand side, was the instrument tower, and the main drift direction for the cases we looked at is essentially from the right. So if we look at a histogram of the types of surfaces that we have here, it's pretty clear. We have just only two possibilities, only bush and only sand that we see here. If we look at the flux footprint, that of course changes with sensor height. So the height of the tower was about 16 meters, and the ratio of the height of the tower to the roughness length, the local roughness length, was about 65. You can do the calculations. But if we had a lower tower, half of that, or one that's quite a bit higher than that, the footprint would change size. And in one instance, for instance, you can see here with a low height that we happen to see mostly sand, a little bit of bush here, and then very soon it's just gray. You cannot see anything. It's just that portion that the sensor sees, translated into a visual. If we go to 60 meters height, then we can see a little bit more. We can start to see the characteristics of Tigerbush, of the banded structure. If we go higher, we can see even more, and it looks a bit like a Fabergé egg or something like that. But not only sensor height, but also stability changes, because stability, of course, regulates how quickly information or changes in the atmosphere can travel up and down. So with near neutral conditions, there's no particular reason for anything in the atmosphere to move up or down, and so it takes quite a long time to get a good probability that particles traveling, starting out at the surface, will actually reach your measurement height, and the footprint is rather large. This is now with one particular sensor height, probably the one in the intermediate one. If you go to more unstable conditions, then you sample a smaller area, and if you go very, very small, where actually the footprint model probably doesn't really work anymore, because it is depends on Monod-Nabokov similarity theory, but it theoretically would become very, very small, and you actually almost see individual square meters or so. So we'll do a little bit of a thought experiment. And if we use this very, very tiny speck of a footprint, as it happens, because of the location of the tower, go back. Here, the location of the tower is actually just downstream of a rather large bush patch. So I didn't put a scale. Yeah, I did put a scale in. That bush patch reaches out to about 50 meters. Okay? So the first 50 meters upstream are almost only bush. Oops. And that is recognized here. You can see right here there is only a tiny speck of bush. But of course, we want to examine the location bias by moving this tower around. If we move it everywhere, what kind of remnant variability will we still see? We're actually interested to arrive at a point where we don't see any variability anymore by moving the tower around virtually. So then we can say if we lose any remaining variability, then we have attained representativeness. So the picture that you see is not the same anymore as before. It's actually slightly blurred, but only by this very, very small footprint filter. And you could see the histogram now looks a bit different. From just the two end members, there has been a distribution of pixels that contain some bush and some sand with this percentage given down there. If we go to slightly larger footprints, you can see it becomes more and more blurred. And two things happen. We remove pixels in the histogram where you can only see bush or only see sand, and move more to the middle ground where we see an average. But it's still, of course, very apparent that we have this banded structure. So we go to larger footprints, and all of a sudden, the majority actually of the pictures go towards something that is an average, go even further, and the histogram becomes more and more narrow, and eventually we'll have a peak that goes around the actual average conditions. And the remaining variance now is only just 5.7%. Here it was still 11 or 12, here 20, here still 50%. But if we go down with larger footprints, the remaining variability or uncertainty from the location of the tower is much reduced. Okay? So here's that location bias using my model FSAM, depend how it changes in this environment with changing sensor height here and with changing stability. This is a negative Zm over L. So we have neutral conditions on the left and very unstable conditions on the right on this one. And here we have different graphs also with different stabilities. So again, neutral conditions are down here, these two curves, and then the higher line curves have more unstable conditions. And of course then the flux footprint is smaller, and your averaging power, the averaging power of the eddy covariance measurement is less. So here, if we decide just arbitrarily that the limit of the sensor location bias is 0.2. Remember, it's a ratio; it has no dimensions. So 20%. Then we can see with stabilities that are near neutral, just about any sensor height is okay. Even the lowest sensor heights here that were actually used. 65 was the ratio of the Zm over Z0. If we go to the stability change, again, the lowest sensor height, the one that's used, is the curve that I made a bit wider here. And you can see that we're staying below this limit for almost all stabilities except the very, very unstable ones. Then we'd have to be worried. But again, this is the limits of this model, so we may be fine anyway, but at least in those conditions, our tool tells us to watch out and see the data maybe with a grain of salt. So this is the summary of this portion. We have this Tigerbush pattern, and that posed the question, if we do measurements there, do we actually see individual pieces of bush? Do we see trees? or do we see the whole forest? We're interested in the whole forest, and we used a footprint model as a tool to examine that. In near neutral conditions, the footprint is rather large. What we see then from the original about 47% to 53% ratio of bush to sand is 35%, 64%. So we can see something that is very close to the entire distribution, and the remaining delta, this location bias, is reduced to only 14%. If we are in convective conditions, Z over L is -3. That is out there. Then we cannot expect to actually have data that are representative of the entire pattern. We should be worried about it then. Go a little bit further. This is actually where I started my work in this, and this is Vancouver. The tower site, the micrometeorological site, is not in the downtown area. It's that would be crazy. It's in a suburban area, and it looks not quite as boring as Mexico City there, but nearly so. And this is the region where Tim Oak, my supervisor then, always talked about homogeneous urban area. Well, there's a park, there's a school building here, there's more parks, and it's not so homogeneous after all. I did field work there a long time ago. Maybe most of you weren't born yet. This is the area. And calculated the footprint, just an isopleth here of the footprint. And the thing is, depending on wind direction and stability over a day, what we actually see changes as well. We didn't take that into account at Tigerbush. That was just kind of a thought experiment. But this is dealing with measurements. So maybe in the morning here, 8 o'clock in the morning, we could say that this is a fairly large footprint. Then it becomes smaller as stability goes down. Of course, the measurement height doesn't change. But we also turn the direction. Now we're almost parallel to this road structure, which may change things. It's not an isotropic distribution of inhomogeneity here. And then we turn again, and towards the afternoon and the evening, the footprint becomes larger again. And so the averaging power at the surface changes over time. It turns with direction. It's small in unstable conditions and larger in neutral even at night than unstable conditions. So it's not the geometric patterns only that are determining the heat flux. Also, for instance, the surface temperature. So we actually commissioned a remote sensing flight to look at the skin temperature determined by an infrared scanner of this surface, and this is what it looks like. And if we look at a sensor footprint from 30 meters height in unstable conditions, then it is blurred to about that. This would be the size of the footprint, and the variability that we still see from that is about 18%. And if we have near neutral conditions, then you can only just about guess that over here is something that looks a bit different, and that's of course this park. Up here are darker areas, and these are these wooded areas associated with these two parks. The footprint there was quite a bit larger. So in unstable conditions, we expect that there may be still some spatial variability, that it actually depends on where we have our tower, that there may be a location bias, but in near neutral or even stable conditions, we can expect homogeneity, and doesn't matter where the tower is. You can put it just about anywhere. I wanted to check this, and the way I did this, I have to go back, well, to here. So, where was this? So this was a tower that was actually in a compound of a power station, a transformer station, and it was here, in this location here. And then I had a mobile tower as well, a pump-up thing that could also go to 30 meters height. And it was mounted on a trailer, and I was able to park it on the side of the street. I did not get permission by the city to put up guy wires across the street and so on, and I did not get permission to park it and operate it without supervision, so I had to babysit this tower for a whole summer. I got fairly good at putting this tower up, instrument it, and then get things going. I timed it, and I got down to 20 minutes from putting on the parking brake to turning the logger on. So that was pretty good. And usually that was done before sunrise so that I could get the entire summer. And what I was interested then is looking at these two towers. One was stationary. One I operated for a week in one location, for another week in another location. I couldn't have 5 towers. We were poor. It was only me to babysit this. And so I changed it around. And what I looked at then was the difference between the two. The scatter plot on the left here is 2 data periods. One where we actually put the 2 systems that we had. These were still one-dimensional sonics from Campbell Scientific, ones that had huge drifts that John mentioned yesterday, and we had to deal with that, of course. Just to give a little bit of history, the data logger was a suitcase about this big and had individual cards in there. If you now program your data logger, we could do that too, but instead of programming it like this, each card was a program unit. And you could, if you wanted to do an average, over 5 minutes, you put one card in. If you wanted to do it over 30 minutes, you put another one in. So we had this assemblage of cards. And then this was a really advanced one because it had 2 ways to access the data, to output the data. It had a little printer, just like from a cash register, you know, that every time it calculated a flux, it would go do-do-do-do. And you could see exactly, oh, what was the flux in the last measurement period? It came out on this paper strip. But then the advancement was that I didn't have to go and digitize that and type it all in. It had an attachment to a cassette recorder. Remember those cassettes? Okay. It actually put analog data onto a cassette recorder. So this was quite advanced back then. We also had something a little bit more sophisticated, but only slightly. So we mounted the 2 sensors on the main tower because I suspected that the relative error between the 2 sensors would increase with the magnitude of the flux. We're looking at QH, sensible heat flux here. And if you look at the dark dots on the right-hand side, it's a little hard to see. You can see there's a little bit of that. When the flux is small, then both sensors, if there's hardly any heat flux, or even slightly negative, then both sensors show that. They're pretty close to 0 here. And if you go to larger fluxes, then there is a bit of an uncertainty between the 2 of them. Okay? So that's quite natural that happens. And of course, I wanted to see how that compares to having the 2 sensors apart. So the open circles are all the measurements that I had of times when the 2 towers were separated by, on average, about 1 kilometer. Sometimes a little less and sometimes a bit more, but in different wind directions as well. And you can see that there's this cone shape, that with larger fluxes, there's also more variability. But of course, with larger fluxes, remember, the stability goes down. We have negative instability. So larger fluxes have more unstable conditions then, or mean more unstable conditions, and a smaller footprint. So your sampling is smaller, and your location bias then is expected to grow. And this was a check whether this actually works. And what I did then, I looked at the spread of the individual measurements between the two. How far apart can they be expected to be? And that's what I plotted on the right-hand side for the calibration period and for the so-called intersite period. If we also had seen a change of this spread between the two measurement systems, a systematic variation with the size of the source area of the footprint, then we would have been in trouble. But we see there's hardly anything. It's very flat. But the intersite period, there's a very strong variation with that. So the variations, the sensor bias, potential sensor bias, we don't know what it is. We just see the difference between the two. So it is related to that bias, but we don't know what the true average is. But at least we see that the difference, the expected difference between the two sensors when they're far apart decreases if the footprint becomes larger. And when I saw this, I thought, yay, my PhD is saved. And it was. So the spatial representativeness goes up towards the right. Moving a few years ahead, again to Morgan-Monroe State Forest. At some point we want to make a break, right? Let's just have a little biological break right here. All right, let's continue. So this forest here, I can't remember what I'm going to talk about. So there's the tower. All right, we'll examine the homogeneity of this footprint, of this tower location. And I do have to say, of course, I had a hand in choosing the location of this site, and I wanted to choose something where we have a chance to have measurements that would be representing something that is representative, that shows the behavior of the whole ecosystem, which was very useful because it is still considered one of the sites where the data are quite easily compared with models. They behave well in this sense. So we did our job right there. We have a tower site that ensures fairly good spatial representativeness most of the time. But I came into this, of course, also with an interest in exploring inhomogeneities. And so I kind of shot myself in the foot because with our measurements, as you'll see, there's not much, but a little bit. It turned out to be never enough that we ever were able to publish something that was of relevance on the inhomogeneities because it was so homogeneous. So on the face of it, it's actually quite an inhomogeneous area because there's quite a bit of topography, and I call this topography sometimes isotropic low amplitude high frequency topography. Think about it. It's not rolling hills. It's drainage channels in all directions. It always goes up and down, so high frequency, or high wave number, rather. It always goes up and down, but never much. The relative topographies are the same order of magnitude as the height of the trees, which doesn't make things easier, I think. Looking at the papers that the two of you have written in the past, that's an interaction, those two scales, that it doesn't make life much easier. So this is where it is, in the south central Indiana. And the main wind direction is from the southwest. In this axis here, so the footprint then would also look in that direction. And there's overlaid here a footprint over a remote sensing image. These are Iconos, I think, fairly high resolution, 1 meter resolution pixels, where we determined NDVI. And so this is a representation of NDVI. Don't ask me about the colors because I can't see almost any of them. What I can see is blue, and the blue areas have almost no vegetation. The rest, I think there's green and yellow, or deep green, dark green, and light green. The darker green would be more vegetation, and the lighter green would be a bit more sparse. But it's actually, as you saw from the picture, it's a fairly closed canopy in most places. So there is in this direction here, where are we? Here's the tower. In this direction, there's the forest headquarters with a parking lot and some buildings, and then there are some small lakes over here. There's also a path and a road, and sometimes you can see this here. Okay, this was for fairly unstable conditions, and then this is for stable stratification. The footprint becomes larger, and of course the wind direction is not always that one. So we, at this time, were asking ourselves, is the tower optimally located, especially with a view to MODIS, because MODIS is an instrument on a satellite that is used maybe still very often by modelers who want to model surface-atmosphere exchange, ecosystem-atmosphere exchange, and the resolution of most of the MODIS products is about 1 square kilometer. As it turns out, it's actually not square, but the area is about 1 square kilometer. And also, you usually have it's not really an aggregate, sometimes it is an aggregate, it goes over every area about once a day, but of course sometimes it's cloudy, and so they provide an aggregate for 8 days. What kind of location bias can we expect? This is the original NDVI. The NDVI variance was some number, and we just called this 100%. And then we filtered it with the unstable footprint, again just with this one axis, the same thing that we did over Tigerbush. And even with the unstable, we see that the remaining variance is now only 28%. So 20% was our margin. So even in very unstable conditions, we just get above this bias limit a tiny little bit. And if we go further, then what the heck happened here? Oh yeah, this is an overlay over both, and you can see the original histogram is quite wide, and then with the filtering it becomes more narrow, as we saw in the Tigerbush case too. But here, of course, we have not just two kinds of pixels, we have many different ones. So actually did this for every hour that we had over an entire month, but we're looking at a particular 8-day period that from MODIS we get one shot, kump. And we're trying to compare this with flux measurements that are going in different directions with changing wind directions, and of course different stabilities. And what I wanted to explore and visualize is, what does a footprint actually look like? What does the flux sensor see, in quotes, over an 8-day period? And you'll see sometimes it's completely dark. When it's completely dark, the flux sensor doesn't see anything. That was because it wasn't working. Or we had to throw the data away from other reasons. Either there was not enough U-star, not enough turbulence, or some other problem. Okay? It looks a bit like someone with a flashlight running around the tower, around the forest. So this was a long time ago, 2001, over a period from August 5 to, well. So it looks like this. It moves around. Sometimes you can see a little bit of structure. You can see something dark in there. And of course, in the center, it's very bright. And the flux footprint illuminates the area around the tower. And what is shown here is the composite for this 8-day period. So this is what, over 8 days, the tower sees of this forest. You can see that most of it is in this direction, actually, not in that direction. Most of it is very homogeneous. You cannot see any differences in. You cannot see any non-forested areas in this area, except fairly far away. This is more than 500 meters away. You can see these little lakes in the parking lot. Sometimes, and that's mostly at night when fluxes are low anyway, you can see something, a little bit of influence from areas further away, more than a kilometer away or so. So from this we can draw some conclusions. Surface patterns impose also scales onto the atmosphere, not surprisingly. The averaging over a pattern unit provides a scale of homogeneity. You can determine how big a unit should I always look at to be representative. If you have measurements that have a chance of being homogeneous, or seeing the surface as homogeneous, they have a chance to be used in more general questions. Comparison with models, comparison with other ecosystems and so on. Because you're looking at the ecosystem and not just individual trees or groups of trees. So this was supposed to be the coffee break, but we've already done a little bit of one. And so I'll go to the next segment, which actually is not going to be very long. So we've mostly discussed about aspects of heterogeneity, flow over inhomogeneous surfaces, fluxes from it from a measurement point of view. But we have not really talked about flow over inhomogeneous surfaces from the flow point of view. So when we have flow over inhomogeneous surfaces, and inhomogeneous surfaces is just about everywhere, right? There's no truly homogeneous surface in the world. What I have here is a picture from a technical note for WMO about sensor placement in complex terrain or inhomogeneous areas. And it just gives a bit of an overview here, that influences of differences of surface conditions happen over a rich variety of scales, depending on whether you look at the entire troposphere, if you look at the whole boundary layer, or lower down. From mesoscale to microscale here. So let's simplify it a little bit and just say we have a succession of different surfaces. I just used 2 textures here, but let's just say they're all different surfaces. So surface 1, surface 2, surface 3, surface 4. And we have no obstacles. We'll just consider that they have different conditions as we move along, and the flow would be from left to right. So what happens, of course, is that you have an internal boundary layer growing, starting at the leading edge of this surface here, where it starts. Low down, you have an area that may be considered in equilibrium already with the local surface. Up here, this boundary layer, or maybe we can look at this one here, this blue internal boundary layer excludes any influence of the local surface. So if you're doing measurements up here, for instance, right where my arrow is right now, you can expect to not, even though you're located above surface type 2, you cannot expect to actually sense anything that any influence of surface type 2 yet. Okay? If you're further down, losing the mouse all the time. If you're lower down, you can expect to see a mix between influences from surface type 1 and surface type 2. And if you're lower down even, you can expect to see in this equilibrium layer that you are actually in an area where you have primarily influence from surface type 2, but not surface type 1. And of course, if you then have surface 1, surface 2, surface 3, a whole hodgepodge of these internal boundary layers will develop, and it doesn't look like this. Of course, it looks much more complex, but we can see individual equilibrium layers if these patches are large enough at the very bottom, and then somewhere up it starts to be like a bit of a soup, and that turbulence itself, of course, creates a mixing and a blending, so that at some point, conceptually, we can imagine if this continues for a long time, it'll all be blended together. And that height where that occurs, if it does, is called the blending height. Above that, you may still have a homogeneous surface layer, or maybe the surface layer is already used up for that, and you may be in a mixed layer. But we're primarily dealing with small scale, relatively small scale variations here. Equal or smaller to something that Matthias showed yesterday with a flight over various types of boreal forest, and there was a Candle Lake in between and other lakes. And you could see that at certain heights you could still see the influence of these surface patches. I'm not sure whether it showed horizontal profiles across this landscape at different heights. I don't think so. But if you went higher and higher, you would see less and less structure, and you would see something like a blending height. So let's look at just wind velocity. Of course, over every patch of that, the wind velocity at the surface must go to 0 and at the local roughness length. And very high up, all those profiles will come together, but in between, they're individual profiles. So we get a hodgepodge of these wind profiles. And especially for modeling, if you need, for the lowest modeling level to determine what the momentum flux is, you need to relate your wind speed at the lowest modeling level to the roughness length, fit in a profile, and then you can determine what the momentum transport is. So which profile do you use? Because you don't have any information about the profile. If this blending height exists, then above that, all those profiles will fall into one, collapse into one curve. What you're really interested in is a representative profile. And the representative profile has one purpose only, and that is to give you the right type of momentum transfer for the whole surface, for the whole assemblage of individual segments of the surface, so that it can be related to a roughness length that is not one particular one, but is actually an effective one, again, with the whole purpose of giving you the right spatially averaged momentum flux, or tau, shear stress. The angular brackets refer to a horizontal average, a spatial average. So that's what we're interested in. Now we need to go step back a little bit. Larry Mart published a paper in 1987 in, can't remember which, I forgot to put it down. I'll add this later on. I don't know how many times this paper has been cited, but a lot. And he looked at the spatially averaged shear stress and came up with this equation, which is in a way a conceptual equation. On the left-hand side, you have the total shear stress, spatially averaged, and time averaged. So the horizontal line above is time average, and then the angular brackets are horizontal average. So we have three groups of terms over on the right-hand side. If we're lucky, the first term might go to 0 if the spatial average of the time average of W indeed becomes 0. So maybe we can deal with that one. But this one is what we're most comfortable with. This is the Reynolds stress, U prime W prime over a time average usually, and then the spatial average of that. As it turns out, in inhomogeneous areas, we're not done yet, because there is a correlation that also does not necessarily go to 0, and that is the deviation, the spatial deviation of the time average of U and the spatial deviation of the average of W, the correlation of that, okay, in the spatial average. And that usually doesn't go to 0, even though we suspected that hopefully the W bar goes to 0 if we spatially average it. But that has to do with the way that we determine the spatial deviations from the average. Okay, so that may still hold. This is what we're really after. And that's the negative of the tau. Now, Fiedler, even a few years earlier, Franz Fiedler and Hans Panofsky wrote a paper on something similar to that in mind, and they coined the term effective roughness length. The effective roughness length that will just denote with Z0 F. And it relates to this profile as the time and spatially averaged mean velocity at your lowest modeling level, or we can also say just at a reference level. They were referring to the lowest modeling level. And that, of course, is then related to the shear stress, the spatially averaged shear stress, or rather U star from it, and with this effective roughness length here that we don't know yet. So it looks fairly simple. There is a problem, and the problem is that the effective roughness length cannot be straightforward determined as an average of the individual roughness lengths. So averaging the parameters does not give you the average flux, because their relationship is not linear. So, same time as the paper of Mart, Peter Taylor came up with an approximation, said, okay, we have these profiles here are in neutral conditions, they're logarithmic profiles. So instead of averaging this linearly, we'll try to move towards something that has to do with the shape of the profile, and we'll do harmonic averaging. And so he came up with this mean Z0 that is not exactly the effective one, but it's an approximation to it that you can determine from the individual Z0s itself. You don't have to know anything about the flow across them. You can just look at the Z0s that you can pull from some estimate from some book or table or so, and come up with a mean that is maybe taking into account the different shapes of the profiles in the equilibrium layer and how it relates to higher up. Okay, so this is kind of a reference estimate that is only dependent on local conditions, the local Z0s, and how you can combine them. Well, we wanted to look at this a bit more, because most of the trouble that we have, and actually most of the reason why Gabi and John and I and Matthias can have a job is that there's an advective term in the equation, and advection is really a bitch. It really screws things up. It's the reason why things are nonlinear. It's the reason why when you do the Reynolds expansion, you get new unknowns instead of simpler equations. But it's also fascinating what's in there, so it keeps us in the jobs. That's the good thing. So we wanted to look at something this problem in a bit more detail. And we, of course, reduced this problem into something that we could handle. So we only look at it step changes in surface roughness, no geometry changes, no other things, just step changes in surface roughness. And we could see that there was a asymmetry in the shear stress response. So we could, of course, calculate with this model, and it's a K epsilon model, 1.5 order closure, for those of you who know what that is. And we scaled, non-dimensionalized the shear stress in a particular way, so that, written up here, using the average of the equilibrium shear stresses for for a homogeneous rough surface and for a homogeneous stable surface with the same forcing high above. That's the average. And then we did this delta tau, the difference from this average. And as it turns out, in this non-dimensional way, then the rough surface has the shear stress of +1, delta tau of +1, and the smooth surface has the delta tau of -1. So we first looked at a step change from smooth conditions to rough at 0 here. This is also non-dimensionalized. We non-dimensionalized the horizontal distance with the rougher Z0. And so you come here with a relatively low shear stress over this relatively smooth surface, and then whoop, something happens. You can actually, if you look very closely, something happens even before you get to this leading edge because of pressure influences, but then it jumps up right away because you come at every level, you come at a relatively fast velocity over higher roughness, and of course then that increases the shear very strongly, and you get a huge increase of shear stress, which immediately would slow things down and then reduce the shear stress as you go along. I should have put in the horizontal lines for plus and -1. You can see this relaxation with a long tail. +1 would be right here, and even at this fairly far downstream, you can see it's not quite, hasn't quite reached equilibrium yet. It would take quite a long time to reach equilibrium. Actually, the way we had the model, it will never reach equilibrium. It's an asymptotic approach. Okay, then we did the opposite. Of upstream is just homogeneous forever, and we come in with over a rough surface, and then all of a sudden, whoop, it becomes smoother, and we come with a relatively low velocity because it was slowed down with the rough surface over a smooth surface, and all of a sudden the shear stress is reduced, jumps down, but then things can speed up, and we get to a recovery of the shear stress, and actually it goes a little quicker at the beginning relatively, and then we get to sort of the same distance from the -1, from the equilibrium far downstream. But you could see the difference in magnitude, and if we took the sum together, we get a surplus shear stress here. So the reaction to step changes like that is not symmetric. In a way, smooth to rough wins out, has a higher effect than rough to smooth. So we were then, of course, interested in this example that I showed before, where you don't only have one step change and the infinity to one direction for smooth and an infinity of rough to the other side. We wanted to see what happens if we have a patchy surface where we have a change from rough to rough to smooth, something that Matthias referred to as well. And then we come to something that then I called surface texture, coming actually from textile industry, where they deal with texture. And there are several different qualities to texture. If we look at the panel on the left-hand side here, we can see, of course, that this, looking just at two possibilities of surfaces, this is a coarse texture with fairly large individual patches, and that means also then the number of step changes per distance is not very much. There may be not much of this chance of this asymmetry, but also maybe the flow can almost reach equilibrium before the next step change is reached. And if we go to finer changes, then of course we have more of these edges, more of these changes, more chance to exploit the asymmetry, but we never really achieve any equilibrium. So you can also see that here you would say this is clearly inhomogeneous. If you move further, the distribution of rough to smooth overall is the same. It's always 50%. The rough fraction, the fraction of the rough surface is always 50% from here to left. But actually there is a bit of a moire pattern there. the screen resolution cannot handle the fineness anymore. Okay, it's almost homogeneous. Then, of course, you can also have differences in magnitude. Here we have black and white, and here we have dark gray and light gray. And if we go further, then the magnitude of this is reduced, so that we call that the depth of the texture. And coined M for it. Here we used lambda as the horizontal characteristic dimension of the variability. So that's the magnitude, and the roughness fraction I already mentioned. And then there is something called the patchiness parameter, which has to do with the coarseness and the fineness of this distribution. And this is the experiment that we did, the numerical experiment, that we had one kind of nucleus of distribution of rough to smooth. We changed that too, of course, but for each of the distributions here we have a 1/3 rough, 2/3 smooth, for instance. We then changed the patchiness of this and see how the flow and how the average shear stress will develop with this experiment. And the way we put together, actually when I say we, it was mostly my graduate student, Daniel Bünzli, who did that. The way we did the modeling is we operated the model, the K-epsilon model, in a very inefficient way, because we got rid of most of the linearizations, because of course the nonlinear character of this whole problem is what we were interested in. And I remember we sat together and said, okay, we'll do a sort of factorization of the whole problem. We have these different, these three different parameters that we want to change, and we came up with a number of experiments that you should do. And of course, that time computers were slower. We had a VAX, which was considered a supercomputer then, and he did the calculation of some of his trial runs. And he asked for a meeting again and said, well, here's a problem. If we want to do the whole program of what we set out to do with all the variations, different steps, varying the roughness fraction, varying the magnitude, and varying the patchiness, the cumulative CPU time that he would need was 1,200 years. And then I decided that I did not have funding for that long. So we kind of had to rethink our problem. Now this would probably, on a PC, it would probably take less than a week or even less than that. But that was olden days. So what we found out is that there is advective enhancement of this Z0 effective, of the effective roughness length. What I have here is different magnitudes of this change. The ratio between the roughness length of the rough and the smooth, just 10 times, then 10 to the 3/4, 100 times, and so forth. And down here we show the ratio of this effective roughness length as calculated by the K-epsilon model to the mean as proposed to by the geometric average or harmonic averaging from Peter Taylor. And we can see that even for 10 times m, we have, here's 1, so this is not quite double, and then we have, up to 10 times, depending on the magnitude of the change, of course, of the roughness steps. The stronger the roughness steps, the more this advective enhancement is increasing the effective roughness length over the locally determined harmonic mean. And there's a bit of a change on where you would determine that with height, but very quickly it becomes constant, the ratio. So we can see with this patchiness, think back of what is actually roughness. The roughness is already, in a way, a statistical representation, indirectly, because it's just an integration limit, but it's a statistical representation of individual obstacles. They can be grains of sand, they can be blades of grass, they can be individual pebbles in a scree surface, or they can be buildings in urban areas. But it's essentially the statistical representation of all these together, of these roughness elements. So Z0 gives you a representation of how the roughness elements affect the flow. With patchiness, you have an enhancement of this effective roughness length that in a way gives you a representation of the statistical effect of the juxtaposition of not roughness elements but roughness patches. So we call this a second order roughness. This is just a figure from our paper from '95 in Quarterly Journal of the Royal Met Society. And of course, what I just showed, when M goes up, when the actual step change goes up, if you have no step change, then that's the homogeneous case. But if you have a larger step change, then of course we expect that the effect goes up. And as it turns out, this is also dependent on the patchiness parameter, but we'll look at that in the next picture here, where we look at the effect of the fraction of the rough to the smooth area. So the rough fraction that can go from 0, where we of course we have homogeneous smooth surfaces, to 1, where we have a homogeneous rough surface. And so this enhancement is expected to go up as we have real patchiness, and then go down again to the smooth limit, or from the smooth limit to the rough limit. And of course this happens, and we have different changes here with different patchiness fractions or geometries, but it's not symmetric. The maximum is not at 50%. So again, rough dominates. A little bit of rough surface dominates this enhancement. This is also shown here, how this enhancement varies with the patchiness parameter. So going from coarse texture to fine texture with lots of changes. And this enhancement goes up, and of course it depends again on this R, on the fraction. Again, if you have almost only smooth surfaces, then it's low. If you have almost only rough surfaces, it's higher. And this crossover is also an indication of this asymmetry. We actually also looked at two different models, the K-epsilon model and also a mixing length model. The mixing length model, as it turns out, overestimates this effect quite large. And I say overestimation because there's a picture I'm not showing. We compared it to data. Someone in Bradley was Australian, right? Were you part of that measurements? Where he had, I can't remember. You're not quite that.
Bradley was my boss, and he actually finally retired a month and a half.
Is that right? Okay. Well, he did some measurements of actual shear stress by looking at stress plates on the ground on an airplane runway, and I'm not quite sure how he did the variation of the stress, the measured stress from the leading edge. But he had a tower, okay. Yes.
And he had roughness, and he moved the roughness.
He moved the roughness. So he had only one flux, one shear stress plate, but he moved more roughness elements ahead of it, or removed them, and that's how he got the variation of this step change away from the leading edge. And that's one of the few data sets that we found, or it's the only data set that we found, where we can compare our measurements. And actually the K-epsilon model fit very nicely, and the mixing length model overestimates that. So that's also an indication that the K-epsilon model is capable a little bit of having non-local effects, but the mixing length model always looks at things locally. And it's only through this non-local effect that also we can capture this advection properly. In the next step, we also wanted to look at not just boring momentum transfer, but actually also scalar transfer. Because often the changes we see in the landscape are not just rough and smooth. Actually, often in agricultural areas, we see fields that maybe the roughness is not that different, but one is irrigated, one is not irrigated, one is already ripe, and the plants have maybe shut down their transpiration already, and the other is still happily transpiring. So wet and dry patches are much more common, or changes in temperature, of course, as well. Here we looked mostly at changes in wet and dry. We had to think to keep some things constant because it was still a numerical experiment, and we decided to keep the available energy constant over this time. It's not very realistic, because usually when you have a wet soil, it becomes darker and available energy will be affected, but we needed to keep some things constant. So also here we can see asymmetry of step changes from dry to wet to dry. This is the point, the dotted line here is indicating the equilibrium, no, not the equilibrium evapotranspiration, but the evapotranspiration that would be in equilibrium with the surface, with that surface wetness. So again, we have an undershoot. This is a cyclic system. Then at the leading edge to the wet area, we have an overshoot and then a relaxation. You can imagine that if we had a much longer patch, it would probably reach the equilibrium somewhere in infinity. And then we had an undershoot again. And we have a similar asymmetry also here. So in this case, the wet patches are the ones that dominate. No, it's the dry ones. This is the wet fraction. So it's the dry patches that dominate, and you can think about why that is. There's advective enhancement also of QE. Anyone who's ever dried clothes outside using the wind knows that if you have your clothes very close together, then they won't dry as fast. And of course, nature knows that too. They actually exploit this by having leaves clumped together in trees so that they protect each other. If they were distributed far away, then you have a relatively low wet fraction, and you would increase your transpiration. And of course, ecosystems have developed in a way, as Nadine told us, to maybe optimize the water use efficiency. So we can see a bit of that here too. And so with that, I just want to make some take-home points. I put together these take-home points late last night, so bear with me. There may be others, but of course there is a panel discussion, and we want to leave some things to the discussion as well. So it's mainly advection, that causes non-local effects over inhomogeneous surfaces. Not talking about communication in the soil. As soon as we have roots involved and lateral flow of water, of course, things become more complicated as well, usually at a different time scale, but nevertheless we should not forget that there is something going on the ground too, we just can't see it. The average surface parameters do not relate to average fluxes, and that's just too bad. It just makes our life hard, but so be it. Surface patchiness behaves like a second order roughness, or in the sense of patchiness of wet and dry, like another pathway of evaporation, virtual pathway. If patchiness extends to, as the pattern of patchiness extends to something that we can call statistically homogeneous, then there might be a chance that we actually reach a blending height. And above the blending height, we then have homogeneous conditions in the atmosphere because of the power of mixing and blending of the atmosphere itself. Now, for the modelers, if the blending height is above your lowest modeling layer, you should actually relate your surface fluxes not to the lowest modeling layer, but to the blending height. That's it.